Hello students, this is section 6.3, proving that a quadrilateral is a parallelogram. Our goal for today is to determine whether a quadrilateral is a parallelogram. This lesson will cover several different ways that we can tell whether or not a quadrilateral is a parallelogram. One of the first ways that we can see that a quadrilateral is a parallelogram is if we have a four-sided figure whose opposite sides are congruent. Two additional ways that we can tell whether or not a quadrilateral is a parallelogram is if an angle of a quadrilateral is supplementary to both of its consecutive angles, and if both pairs of opposite angles are congruent. So the first type of question that we might see will give us this algebraic situation where we need to determine the values of variables that will make a figure a parallelogram. So based on one of the previous theorems, we know that in order for this figure to be a parallelogram, the opposite sides must be congruent. So what we want to do is we want to set these algebraic items equal to each other. So I'm going to set one equation as 3x minus 5 equals 2x plus 1. I'm going to write the other equation as y equals x plus 2. The first equation is in a single variable. So I'm going to go ahead and solve this multi-step equation. Subtract 2x from both sides. By doing that, I get x on the left. And at the same time, I'm going to add 5 to both sides. And we'll see that 1 plus 5 is 6, so we know that x equals 6. Now that we know x equals 6, we can say y equals 6 plus 2, and therefore y equals 8. So this figure is a parallelogram when x equals 6 and y equals 8. So the other type of question we might see is algebraic expressions for the angles. In this case, we want to set either opposite angles equal to each other or consecutive angles supplementary. Most often, setting opposite angles equal to each other will result in an equation that is always true. So in most situations, we want to set consecutive angles to be supplementary. So I'm going to set 3y minus 2 plus 4x plus 13 equal to 180. So we have 3y minus 2 plus 4x plus 13, and that's going to equal 180 degrees. A second equation that we can establish here is 3y minus 2 plus y plus 10 equals 180 degrees. So 3y minus 2 plus y plus 10 equals 180. We could establish other equations, but this second one is fairly easy to work with because you can see the equation only has y's. So we can solve this for y. 4y plus 8 equals 180. Subtracting 8 from both sides, we get 4y equals 172. And therefore y equals 43. Once we know the value of y, we can once again plug it in up here. So we have 43, and the remainder of the equation stays the same. So 3 times 43 minus 2 plus 4x plus 13 equals 180. So here we want to multiply 3 times 43. 3 times 3 is 9. 3 times 4 is 12. So we have 129 minus 2 plus 4x plus 13, and that's supposed to equal 180. So combining like terms, 129 minus 2 is 127. 127 plus 13 is 140. So we have 140 plus 4x equals 180. Continuing this down here. Subtract 140 from both sides. We have 4x equals 40. and therefore x must equal 10. So another theorem, again the opposite of something that we learned in 6.2. If the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. One of the things to note about this theorem is they don't have to be of equal length. Segment BE has to be the same as segment ED. However, segment BE does not have to be the same length as segment AE. So let's prove this. If segment AC and segment BD bisect each other at E, what that tells us is that this length is the same as this length, and that AE is the same length as EC. So one of the things that we can do is we can separate these triangles in order to get a closer look at them. So one of the things that we should take note of is the vertical angles that we have here, and we have another set of vertical angles here. So if we separate triangle AEB and triangle ECD and we remark them, we can see that the vertical angles give us the one angle marked green. The blue segments are on one side of the green angle, and the red segments are on the other side of the green angle. So in this case, we can say that these two triangles are congruent, and we can say that they're congruent by side angle side. Separating the other triangles, we have one triangle BCE that looks like this, and we have another triangle, triangle AED, that looks like this. So again, the vertical angles, probably a good place to start. We have AE, which is congruent to EC, and we have segment BE, which is congruent to segment ED. So once again, we can say that these two triangles are congruent by side angle side. Once we have triangles that are congruent, one of the best things that happens is CP/CTC. So now that these two triangles are congruent, CP/CTC tells us that these parts must also be congruent. And for the same reason, we can say that these parts are congruent also. So here we have a four-sided figure whose opposite sides are congruent, and therefore it must be a parallelogram by one of our previous theorems. Our final theorem is the only one that isn't an exact opposite of a theorem from 6.2. It says that if one pair of opposite sides of a quadrilateral is both congruent and parallel, then the quadrilateral must be a parallelogram. So we want to decide if a quadrilateral is a parallelogram with some given information. Here we have segment AB equals 5, segment CD equals 5, the measure of angle A equals 50, and the measure of angle D equals 130, and we're asked to prove that this is a parallelogram. In this case, one of the things that we should always be looking for is parallel lines. We're looking to show that this is a parallelogram, so if we can get parallel lines, we're almost there. Because of angle A and D's relationship, we can see that distinct C shape that we remember from chapter 3. These are same side interior angles, and they do in fact have a sum of 180. 130 plus 50 is 180. Because of that, AB is parallel to DC. And so now the theorem that we just looked at, we have opposite sides that are both parallel and congruent. So this is in fact a parallelogram. In this case, we have segment EF, which is congruent to segment GD, and DE parallel to FG, and we're asked to prove that this is a parallelogram. In this case, this is actually not necessarily a parallelogram. It could be, but does not have to be. So one of the things that I want you to realize is sometimes we have to draw things that aren't there to see this. So in this case, we could add this to the diagram and we could say, what if F was really here? What if F was not there and EF is still the exact same length? Segment EF is still exactly the same as segment GD, and DE is still parallel to FG, but this is no longer a parallelogram. So this one is not possible. And the reason for that is having parallel sides with the other pair of sides congruent does not necessarily show that a quadrilateral is a parallelogram. So here we're asked to show that LAND is a parallelogram. We're given some congruent sets of angles. The nice thing about this, one of the things that you should remember from proving triangles congruent, is that LN is a reflexive side in both triangles. These triangles are actually congruent by angle, side, angle. So we have triangles that are congruent by angle, side, angle, and therefore CPCTC comes in and tells us that all their parts must be the same. So these parts are the same as these parts. Because of that, we can certainly say that this is a parallelogram because its opposite sides are congruent. Here we're asked to show that HIJK is a parallelogram. And this is another example of a situation where this is not necessarily a parallelogram. It looks like it could be, but the only way that this is a parallelogram is if opposite sides are congruent. In this case, we can see that HI is not necessarily the same length as KJ, and KH is not necessarily the same length as JI. So this could be a parallelogram, but based on this information, it's not possible to tell. Finally, we have a word problem. It says a truck sits on the platform of a vehicle lift. Two moving arms raise the platform until a mechanic can fit underneath. And we want to know, why will the truck always remain parallel to the ground as it is lifted? In this case, the primary reason why this remains a parallelogram is because no matter what happens, the opposite sides of this quadrilateral remain congruent. So this graphic shows all of the methods that we know to show that a four-sided figure is a parallelogram. It starts with the definition and goes through all of the theorems that we learned in this lesson. That concludes section 6.3, proving that a quadrilateral is a parallelogram. Don't forget to take the quiz, and I'll see you tomorrow.